Introducing the binary isomorphous system, in which the term binary refers to the presence of two components in the system. And isomorphous refers to when two components, both liquid and solid phases, can undergo complete solubility and dissolve. From this phase diagram, we can see there is two single-phase regions present, liquid denoted by L and solid denoted by alpha. And the two-phase region, highlighted in yellow, being solid plus liquid, denoted by alpha plus L. These phase areas are separated by the liquidus and solidus line, in which the curve here, highlighted in orange, is the liquidus line that separates the liquid phase from solid plus liquid, and the solidus line here, highlighted in green, separates solid from solid plus liquid. A good example corresponding to this is the nickel-copper solution, NiCu, where the criteria for solid solubility is its crystal structure, electronegativity, and radius. Since both nickel and copper have the same crystal structure, face-centered cubic structure, FCC, and have similar electronegativity and atomic radii, there is high mutual solubility, and hence both is totally soluble in one another in all proportions. Therefore, it is an example of a binary isomorphous system.
Hi, and now I would like to talk about the binary isomorphous system. So there are three rules for binary isomorphous system, which in the first rule is that we can determine the number and types of phase present through temperature and composition given. For rule 2, it states that we can determine the composition of each phase through temperature and composition given. And for rule 3, we are able to determine the relative fraction through temperature and also composition given. So for rule 1, through temperature and composition given, we can determine the number and types of phases present. For example, at point A, which is 1100 degrees Celsius and 60% by weight, then we'll get one phase, which is the solid phase. At point B, which is 1250 Celsius with 35% by weight, we'll get two phases, which is liquid phase and solid phase. So for rule 2, through temperature and compositions given, we can determine the composition of each phase present. For example, as we are given the compositions as 35% by weight, so at temperature air, which is 1320 degrees Celsius, we'll get only liquid phase, where the compositions of the liquid will be same as the compositions given, which is 35. And at temperature D, which is 1190 degrees Celsius, we'll get only solid phase, where the compositions of the solid will be same as the compositions given, which is 35. At temperature B, which is 1250 degrees Celsius, we get two phase, which is the solid phase and the liquid phase. So to determine the compositions, we need to draw a tie line, which is a line connected between the solidus line and the liquidus line. So the composition of the liquid will be 32% by weight, and the compositions of the solid will be 43% by weight. So for rule 3, through temperature and compositions given, we can determine the amount of each phase in percentage by weight. So for example, we're given the compositions as 35, and at temperature A, where there's only liquid phase, the percentage by weight of the liquid will be 100%. And at temperature D, which is only solid phase, the percentage by weight of the solid will be 100 as well. And at temperature B, which is both solid and liquid phase, we can calculate the percentage by weight using the lever rule, where we'll take the length of the opposite side divided by the total length of the tie line. For example, the percentage by weight of the liquid will be 43 minus 35 divided by 43 minus 32, which then will get 73% by weight. And using a standby, we'll find the percentage by weight of the solid to be 27%.
Hello, I'm Louisa, and today I'll be explaining to you the development of microstructure in isomorphous system. So today I'll be using copper-nickel alloy as an example. So at temperature of 1300 degrees Celsius, the microstructure is 100% liquid phase. So for the phase composition, it will be 35 weight% nickel, and the phase amount will equal to 1. So at temperature of 1270 degrees Celsius, which is just above the liquidus line, the microstructure is mostly in the liquid, but the alpha phase will begin to nucleate. So the alpha will represent the solid phase. And the phase composition, which can be found using the tie line, for liquid it will equal to 35 weight% nickel, and for alpha it will equal to 46 weight% nickel. So in order to find the phase amount, we can use the lever rule method. In this case, we will have to use R to represent liquid and S to represent the solid. So in order to find the phase amount of liquid, we can use S over R plus S, and similarly, we can use R over R plus S to find the phase amount for alpha. So using the lever rule method to find the phase amount, it will result in 0.99 for phase amount of liquid and 0.01 for phase amount of solid. A simpler method would be to take the phase amount of liquid, subtract from 1, which will give us the same result for phase amount of solid, which is 0.01. So moving on to temperature of 1250 degrees Celsius, there will be more alpha phase that will develop, and the phase composition, which can be found using the tie line. For liquid, it will be 32 weight% nickel, and for alpha, it will be 43% nickel. So for phase amount, using the lever rule method, the liquid phase amount will equal to 0.70, and for alpha, it will equal to 0.27. So moving on to temperature at 1225 degrees Celsius, the microstructure is mostly in the alpha phase, but there will be some liquid that will still remain. So the phase composition will be 24 weight% nickel for liquid and 36 weight% nickel for alpha. So the phase amount for liquid will be 0.08, which has significantly decreased, and for alpha it will be 0.92. So lastly, at 1200 degrees Celsius, the microstructure is finally all in the solid phase, and the phase composition will be 35 weight% nickel, and the phase amount will equal to 1. Thank you for listening.
Hello everyone, my name is Yinti and I'm here to present the last few slides for binary isomorphous system. So what is the main differences between a core and equilibrium structure? In equilibrium process, the composition of the phase form is uniform throughout, but in a non-equilibrium cooling process, the first solid formed may have a higher solid composition than the next solid that forms, leading to a formation of a core structure. Equilibrium cooling gives us a desired microstructure and is the process normally used in industries to make metal bars from their molten state. Sufficient time is available for the solute to diffuse in equilibrium cooling, but in non-equilibrium cooling, there is no diffusion of solute. In equilibrium cooling, the cooling rate is so slow, whereas non-equilibrium cooling process has a higher cooling rate. Because cooling rate is too fast for the materials to readjust compositions and diffuse uniformly, it leads to a core structure. For example, according to the diagram, the first solidification occurs at 46 weightage% of nickel, and as cooling rate is rapid, the first core is formed before the last solidification occurs at 35% weightage% of nickel. Hence, there are multiple cores of different weightage% of nickel in the microstructure as they solidify before readjusting to the next nickel composition. On the other hand, there are no cores in the equilibrium structure as there is sufficient time for uniform diffusion at the different solidification temperatures. Moving on, I'll be talking on to the mechanical properties in a copper-nickel system. For the tensile strength graphs, Tensile strength increases as the weightage percentage of nickel increases till it reaches its peak at around 60% of nickel, before gradually decreasing to 350 million pascals at pure nickel. As for the ductility graph, as weightage percentage of nickel increases, the percentage elongation decreases until it reaches its lowest point at around 55% of weightage of nickel, before increasing until 50% of elongation at pure nickel. Thus, according to the two graphs, when the copper-nickel system reaches its highest tensile strength, its ductility is relatively low, and vice versa. Thank you. This is the end of the slides of explaining the binary isomorphous system. I hope that after watching this video, you guys understand more about it. Thank you.